Good. Yeah, good afternoon. Inbal and I are talking today about graph substitutes. It's a topic I really like. And I think for one, it would be a nice introduction to combinatorial auctions and Valuated equilibrium. And it would also be an interesting thing if you're interested in convex analysis. Even if you don't care about auctions, I hope you'll get some interesting combinatorial algorithms from it. So the reason I really like this theory, it has actually a very interesting story. So they started as like 3 different communities, studying 3 different problems that apparently had nothing to do with each other. So the earliest of them was in economics. So Kelso and Crawford was trying to understand what's the necessary and sufficient conditions for market equilibrium to exist and for prices to converge to something that clears a market. There's a problem in economics. They come up with this notion called graph substitutes. So in parallel, Dress and Wenzel, they were studying number theory. There's something in number theory called the Grassmann-Plucker relations that has to do with some discrete version of the determinant. And they were trying to generalize those notions. They came up with things called Valuated Matroids, Matroidal maps in that context. And in Murata and Shiora, they were trying to generalize convexity to discrete domains. So they were trying to think that convex functions are really nice things. We understand convex functions on real numbers. What does it mean to be convex on the lattice? And on sets of bases of matroids. It turned out that they were really looking at the same problem. It took a long time to realize. It took like more than 10 years. And eventually there's a theorem saying that those class of functions are actually the same thing. Graph substitutes are also the concave functions and also the matroidal maps. And I think the work in actually providing the glue is like beautiful theory that pretty much Murata showed other people, especially in Japan, are trying to come up with this theory called discrete convex analysis. And I think the way Murata tries to likes to phrase it is a combination of matroid theory and convex analysis. So what I'll do in the beginning, I'll go over those 3 different problems and tell you what those people are asking, and then I'll show the equivalent and try to use the equivalence for doing interesting things. So let me do some notation to start. I call goods, but it's really items. There's n items. It will be our base set for everything, just n is 1 to n. Simple, and then we'll look at valuation functions. So the valuation functions define the systems of subsets. So 2 to the n is like all subsets of n. You can also think as a function of the hypercube. Given prices, or given, I'm using market terminology, but given a vector of real numbers, you can define the v subscript p is v is the value for those goods. V subscript p is the value of those goods if you need to pay p for those goods. So v of the value of s and p of s is just, we have a real number and an index, just the sum of prices or sum of real numbers in that set. Again, using economic notation, we're going to talk about demand correspondence, which means that given a v and a p is the bundles you prefer. So if you're faced, if v is your value for the set of goods and p is the price, dvp is what your optimal bundle, which things you would like to buy. It's the set of goods maximizing v of s minus p of s. And we talk about how do you access these functions. One is the demand oracle. Saying the demand oracle, you're going to think of something I can call with some vector of prices and a valuation function to return the one set that's demanded. And the value oracle is just like evaluating the function at s. I often talk about marginals, how much he values s if you already have t. So it's how incremental value you get from getting additional set of goods s. All right, so what's Valuated equilibrium? This is a very old notion, which means what it means for a market to reach equilibrium. So a market is just some set of buyers and a set of goods. The buyers have valuations. So valuations just functions that map subsets of goods to some value. And if I put prices on the items, so if every item has a price, the buyers have demands, which says the favorite bundle under those prices. And you see that it's equilibrium if I ask every person to pick their favorite bundle of goods. Say under those prices, she prefers to buy the apple and the orange, she prefers to buy the lemon, Victor prefers to buy nothing, and for appetizers with grapes, cherry, and bananas. And if that happens, so if everyone demands the every bundle of goods, everyone can get what they want, so there is no conflict. And we clear the market, so it means all the goods are sold. Then we have something we call Valuated equilibrium. So that's nice. It's something that we imagine markets reach equilibrium. Once this happens, everyone's happy. Things are sold nicely. And what's nice thing is that there is this theorem saying that if you are in market equilibrium, so that's as a definition, every good is demanded by exactly one buyer. And one nice thing is that if you are in equilibrium, then welfare is maximized. So the sum of if you reach something, if you have some vector of prices that everyone demands the favorite bundle and everything is sold, then you found the partition that actually maximizes summation of VISI. So the proof is very easy. The proof is just like LP duality. If you've seen this proof, we'll see this proof probably later on the slides, but it's just like, just put a one line, but you can come up with it. So that's nice. So equilibrium is an interesting thing, if anything, to compute this, the solution to this problem. There was a problem that Kelsen-Crawford will look is when do equilibrium exist? And maybe a slightly more challenge is do markets converge to equilibrium prices? How do the markets work? And we can ask ourselves as computer scientists, how do we compute a Valuated equilibrium? Okay, so the way they approach this, I actually like the paper very much. The way they approach this question is, to me, a very natural way to approach this question. So they let me write an algorithm, imagine a natural algorithm to compute equilibrium, try to analyze, with the point that I can no longer analyze, I just impose the condition that makes my analysis go through, and that's what they call gross substitutes. I've done it multiple times in my papers, but I'm glad that famously put it also. So what's the algorithm they propose? The algorithm is actually quite old. It was proposed by a French economist called Walrasian. It's called Valuated tatonnement. And Walrasian observed this thing that the natural thing for markets to do is that they will look at the items. If there is if the items are over demanded, so more people want the items than you have supply, just increase the price and demand will go down. If the items are under demanded, so no one likes it, decrease the price and someone will buy. And if we keep doing that, eventually we'll reach equilibrium. That was like a heuristic that he came up with. And that's what tatonnement is. Tatonnement is not doing the French word, but let's say, if you were to speak that in French, it means try and error. Just like keep trying, keep adjusting this price, that eventually things will be fine. So what Kelsen-Crawford did, they analyze it. And let me show what the mechanics of tatonnement is. Here I'll just increase prices. So what Vara said is increase and decrease, but let me just increase for now. So we start with all prices to be 0. Initially I'll give all the items to the first buyer or to some arbitrary buyer. See, everything is allocated to S1, everyone else gets nothing, and now the price is 0. And now at this, every point, I will ask, is there any buyer that's unhappy? Is there any buyer that's getting a bundle that's not in the demand set? And if someone is unhappy, if everyone is happy, I'm good. I'm in equilibrium. I'll stop. If not, I'll pick this buyer. I'll find the items that some set that he likes, and I allocate to him. And I increase the prices. So let me tell you formally what it is. There will be a global vector of prices, P1 to Pn. And I will slightly personalize the prices in a very, I will say slightly because I will say Pi, the prices that I can choose from. This is just to make the analysis easier. You don't really need that. But I'll say that if you currently holding an item, so if J is in your set, to keep the item, you just need to pay Pj. But if you don't have the item, you really need to pay Pj plus epsilon, some small epsilon, to acquire it. Right, so that's Pi. That's the personalized price. The global price is what you pay for what you have. To what you don't have, you really need to face a slightly epsilon increase. So while there is someone that's not happy, that would prefer to acquire some other goods that other people have, we pick these goods and assign to him, and also increase the goods from the prices that he acquired by epsilon, and then he will be happy. So you ask V1. V1 is definitely happy because she's getting everything and paying nothing. but maybe now V4 is unhappy. She'll say, okay, for those prices, I like the cherry and the banana because it's 0. So okay, it's going to say, first I increase the price to epsilon, and I'll give her and remove items from V1. Now maybe V3 said, okay, for those prices, I'll prefer to get the grapes and the cherry. I'll increase those prices, and I'll give that to him. Now V1 might say, okay, I'm no longer happy, now I'd like to get the grapes. I'll give that to me. Increase the price of the grapes, I'll give that to her. And if I ask and no one else wants to, and at this point I may ask, okay, is anyone want to change? Maybe if they don't want to change anything, you're good, we're done. So that's a very natural procedure. It's like how something that you could even imagine markets could do. Okay, so that's it, yeah. First, the process always ends. The process always ends because price cannot go on forever. If the price become like super high, no one will want, they will be happy with getting nothing. So the process stops. When it stops, everyone is happy because everyone is getting some item in their demanded set under this like slightly personalized prices. But you can even make them like to the global price. It's usually just a thought process. In practice, what you do is just pick this epsilon tiny, 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 send to 0, so everyone will get a bundle on the actual global prices. So it seems like we are in a version equilibrium, but we are missing one thing. We are almost there. So what else do we miss? So there's a natural condition. One condition we miss that we need to sell everything, right? So otherwise, there is a very simple equilibrium that you just set the price really high, no one buys anything, but it's not an equilibrium because the market doesn't clear, you don't sell. Everything is sold to exactly one buyer. So the condition that's missing is that every item is allocated. And if you come back to the previous algorithm, you can ask, what do you need to keep every item always allocated? And what we need is really that once someone asks for a bundle of items, everyone says, okay, I am unhappy, give me some items. The items that he asks for is a subset of the item that he currently has. The xi is a subset of si. If the valuation is such that they always ask for a bundle that's a subset of what they already have, then we can run this procedure and always keep a partition. So then I think the approach of Carlson-Crawford, okay, let's define the class of evaluations have this property. So that's the definition of gross substitutes. So evaluation is gross substitutes if for all vectors of prices p is smaller or equal than p prime, if you wanted something at the lower prices, so if S was your favorite set at the lower prices, if now the prices increase, your favorite bundle contains the bundle of the items that did increase in price. So let me repeat, this is a bit confusing, so let me go over that one more time. You bought some goods. Let's say you bought some goods, you bought some potatoes, some bread, some butter, and so on. Now the price from potatoes increased. If before, whenever the price of the fact that the price for potatoes increased shouldn't affect the demand for carrots. If you wanted carrots with that price, the fact that the price for potatoes increased, it shouldn't affect the demand for carrots. It's maybe not like bread and butter, for example. Maybe if now the price for butter increases, all of a sudden you don't want bread anymore. So they say that it substitutes if, then again, given two vectors of prices, if you wanted those goods, if it was your favorite goods until the lower prices, whenever the price of some good increases, you still want, in some set, the goods for which the price didn't increase. Right, so that's the definition that actually makes the algorithm work. And under this new definition, the algorithm always keeps a partition. And at this point, the theorem writes itself. You can write, there is always a variation equilibrium evaluations of gross substitutes, because you can just run this algorithm and arrive at equilibrium. So good. Theorem, GS valuations, variation equilibrium always exists. But is that interesting? So one criteria for saying that that's interesting is because there's many functions we like and we care about that have this property. Simple functions like additive functions, like say the value of some bundle is a sum of values of each individual item. Unit demand, which is that the value of some bundle is the maximum between the values of the bundle. Also, this nice class called matching valuations. So if you have, those are your goods, and X is some set that, I don't know what is, but like some arbitrary set, and Wij is like some weights. if you have a set S of goods, say 2, 3, the maximum matching from 2, 3 to X would be the sum of the weight of the two edges that maximizes, and it's a matching, will be the V of S. And similarly, if it's 1 to 3, maybe the matching is different. And this is actually, economists really like it because it's they talk about job market allocation. Let's say there's a bunch of positions that you have in a firm. There's a bunch of possible workers you can hire. That's the value of having those workers assigned to this position. And you cannot assign two workers to the same position. What's the maximum value you can get off those workers? That's what they usually in contract theory, they like to talk about as matching valuations. Good, so that's a nice class. It's a good, interesting class. And then also there is matroid matching. Is the same thing except that I also have some matroid constraint here. The set of endpoints here must form an independent set in a matroid. So if you don't know what's a matroid, or it's not, it will become important later, but then I'll explain later what's a matroid. An open question that to show a GS function that's not matroid matching. I think that's open. We don't know anything. All the functions we know are in this class, so I cannot prove they are not in this class. So it's I think it's a nice. I actually like this question very much. I'll come back to this question later on. Okay. So one reason it's interesting is a lot of interesting examples of functions that are gross substitutes. But another reason it's interesting is because this characterization that at least when I saw the proof, it looked hacky because it's what makes the algorithm work. But it's also tight. It turns out that if you have a class of evaluation functions that contain unit demand, and variation equilibrium always exists for this class, then this class must be a subset of gross substitutes. So that's the largest class that contains unit demand evaluations that variation equilibrium always exists. In that sense, okay, maybe we're onto something here because somehow it's a tight result. So that's variation equilibrium. Let me give you a different problem. Now, a different problem, different context. This is like Dress and Wenzel. They were studying like this problem in number theory. There are some vectors in Qn, so Q is irrationals. And they were looking at this like this question in algebra and number theory that given a phi of vector, like n vectors, you say it's n if the determinant of this of the matrix by using this vectors as columns is p to the minus n or a over b. So p is a prime. Let's say a over b is two numbers that are not divisible by p. So yeah, so it wants pretty much like what's this highest exponent of p you can get by arranging those vectors in a matrix. So the question is, I give you a set of vectors, find n vectors that if I arrange in a matrix, the determinant to have the highest possible p coefficient. I don't know why this problem is important, but an interesting thing that they realized that there is some relations in non-algebra called Grassmann-Plucker relations, and the solution is via a greedy algorithm. The solution is that you start with any n vectors that are linearly independent, so that the determinant is different than 0, and you go from v1 to vn. Replace v1 by the vector that makes the determinant increase the most, or rather the phi value increase the most, or actually decrease the most because I'm trying to minimize. And if you do one pass of that, doing the greedy algorithm for every v, you get the optimal solution. Which I thought was really nice. It's really surprising to me. But there were, and then they were asking like, okay, which other functions have the same property? Which other functions are defined under subsets of size k, such that greedy is optimal? And they call this valuated matroids. So valuated matroids is a little different than what the object we're interested in because they're defined on sets that have all cardinality k. But let me look at some related notions. So valuated matroids and matroidal maps are very related. They are pretty much, you can reduce one to each other. But a matroidal map is a evaluation like we're interested in defining a set of subsets of n. And you say it's matroidal if for every p, every vector of real numbers, the problem like the one we're interested in, dvp, can be solved by the greedy algorithm. So it means I start with the empty set, I look at the item that maximizes v of I minus p of I add it, and then for every new it, I keep adding the element that maximizes vp the value conditional price of I, condition that I already have ST. And I stop when no longer I can increase this number. And if for every P the greedy algorithm is optimal, I'll say that this map is matroidal. And the reason it's called matroidal is that it's very similar to what a matroid is. So a matroid is a subset system, so a set of subsets that for every, again, vector P, the problem of maximizing P of S, so that S is in the matroid, can be solved by the greedy algorithm. That's maybe not the definition you saw, but that's a complete equivalent to the definition you're usually most used to. That's a nice problem. Let me go to the third thing, which is discrete concavity. So discrete concavity, the idea is that you want to get generalized convexity or concavity to a discrete domain. So for Rn, if you have a continuous domain, the definition of a convex function is the following. You can say the function is convex if for every vector p, all the local minima of f of p, fpx, so fp minus a linear function, is also a global minimum. So this function is convex. You see that the only local minimum is here, all local minima are global minima. The second function is not convex. Every local minima is still a global minima, but it's actually, oh no, there is some little thing. But even if you didn't have that, you could find some linear transformation. So subtract by p of x, such that you have two local minima, two separate local minima. Right, so that's a perfectly valid definition of convex function. That's not the definition you used to. Perhaps you are interested in inequality, but that's completely equivalent. And convex functions are nice, and we really like them in optimization because they're the functions that your gradient descent converges. They're somehow the functions you can run sort of a greedy type algorithms. You can just follow the direction of maximum increase or decrease, depending if you're trying to optimize or maximize or minimize, and you get to the global minimum. So this is nice. And now you're interested in extending maybe to the hypercube or to the lattice or to some other discrete set. So on matroids, this definition extends nicely. You can say that the function is discrete concave if for all vectors p in Rn, the local minima of Vp are exactly the global minima. So it means that if you have some point, if you arrive at some set that you cannot increase the value by adding an element, the first line, you cannot increase the value by subtracting an element, and you cannot increase the value by swapping an element that's in by an element that's out. So add an element and subtract an element, then this is optimal. Then that's the optimal set. So the similar definition of, so that's the definition of discrete concave functions. And Murata has this initial, is the first that defined this class of functions. He called M-concave functions. M-concave functions are functions kind of like valuated matroids that define of sets of the same cardinality. But there is this extension by Murata and Shora that define M-natural concave functions defined on any set. In some sense, if you are into convex analysis, you might be recognizing, I'm talking about something called differential dual without actually mentioning the word differential dual. So Inbal is talking about that, so you see that in part 2, a little more differential duality. But what I'm describing here is really differential duality without actually saying the names that we don't have too much notation. All right, so it turns out that this is all equivalent. So the functions that gross subsystem functions that generally make necessary and sufficient conditions for markets to converge are exactly the functions that are discrete. M discrete functions, and they are exactly the class of matroidal maps. And it's really nice because after many years, this turns out that all those areas the people are studying, they turn out to be the same thing. And you get some nice consequences. For example, you can solve the demand problem in polynomial time. Because if you want to ask what's your favorite bundle of goods when the price is P, since it's the same thing as matroidal maps, for example, you can just run the greedy algorithm. You just add one by one until you can no longer prove that's the optimal bundle. And the proof goes through some techniques called discrete differential equations. So each of the one way that I find to recognize those things are equal, you can actually try to write a differential equation saying when do the functions satisfy each of those properties, and you know that they satisfy the same differential equation. So let me say what's the differential equation now. So given a set function, I will define something called discrete derivatives. The discrete derivatives in direction I, it's very simple things actually. It's a fancy name for simple things, just like the marginal of I, how much value I adds to the set. So the first discrete derivative is defined on the subsets that don't contain I. So the discrete derivative of v in I, condition S, is v of S union I minus v of S. On the other hand, like the usual derivative is also the same thing. You just increase one coordinate a little bit and then compute the difference divided by how much you increased. It's another name for marginals. But it becomes interesting when we actually apply it twice. So you can talk about second order discrete derivatives, which is the derivative with respect to ij, just derivative with respect to I, and then derivative with respect to j. So this will be this expression. You probably recognize this expression from somewhere. This from like the definition of submodularity. This essentially means that the second order discrete derivative is smaller or equal than 0. And you can go and you can ask for each of those classes, give me a condition in which this function is like that. And you arrive, if you do each of those exercises, which is each of them is interesting in their own right, you arrive at something like that. So this RGP equation was done for Gauss substitutes, but if you do for any of the other classes, they did in their respective lines of study, and they realized they are really the same equation arrive. So it means that the derivative ij of v is smaller or equal than the maximum derivative of ik in kj, and that's all smaller or equal than 0. So this simple equation, if you check for every ij and for every set S, you have a Gauss substitutes. It is a condition of the discrete Hessian. So it means that what I call Hessian usually convex not in convex but in analysis in general is like the matrix of the second order derivatives. And here you can imagine you have the similar matrix. You have a matrix of the second order discrete derivatives for every set S. And if the Hessian has this property, you're Gauss substitutes. One interesting thing is that if you, for matroids, for example, one that's actually for matroids is matroidal maps. If you matroidal maps should at least contain a set of matroids, right? So at least you can if you write down these conditions for a function at 0 in a certain set and minus infinity outside, so it's an indicator function of some set, you realize that you recover pretty much the original definition of matroids, the definition of matroids that are most the exchange property. That's pretty much a version of the exchange property of matroids for real valued functions. So for Gauss substitutes, and now what is here in the second bullet point is it's sort of an idea on how you can prove that Gauss substitutes is equivalent of this discrete differential equation. So the proof goes in 2 steps. So it says that if a function is Gauss substitutes, if you still demand some goods at some lower price, the price of some goods increases, you demand the goods at the price didn't increase. The first step is show that if this property is true, there shouldn't be any price such that the only things demanded at those prices are S, some set and some set times a pair, or some S and K and S and ij. So one direction is easy. If somehow you have some price that this is true, it's clearly not Gauss substitutes. Because if it's like that, I just increase the price of j a little bit, and all of a sudden there is no S will be the only set, and there is no longer something that I would and I no longer can aid. So that's definitely not Gauss substitutes. In that case, also easy. If you have some set of price such that it's the only bundles that demand are S and K and S and ij. Again, I just increase the price of j a little bit, and all of a sudden you don't want I anymore. The converse is also so one direction is easy. If there is some certificate like that, it's definitely not Gauss substitutes. But if it's not graph substitutes, then you can like massage the prices until you get some certificate of that type. In the fact that you don't have a certificate of that type, now the second part of the proof that if you don't have a certificate of that type, then the equation above must be true. So the first, this means some modularity pretty much. That so modularity means you cannot give a certificate of that type, and this first inequality here is the certificate of that type. So that's the proof, and you can also, for discrete convex functions, you can also do similar analysis and show that you again recover that differential equation. All right? So nice. So that's the first part of what I want to tell you. That's about combinatorial properties of such functions. The second part of what I'm telling you, second part of the first part will be about algorithm, how to use this property to design algorithms. And I don't know if you have any questions at this point or anything, because I can, while I drink water, you can actually. All right, so let me go on. So I'll use some of those tools we developed in the beginning to solve some problems. So one interesting problem is a welfare problem. So given m functions that have graph substitutes, how to find a partition that maximizes welfare? So how the second problem is that the slightly easier problem maybe is that I give you a partition, you should tell me if it's optimal or not. And the third problem is now I give a partition, I promise it's optimal, and can you find variation prices? So can you find prices that everyone demands those goods at equilibrium? So the hardest, and then you go to easier problems down. So I'll solve them from bottom up. And one interesting thing is that there's many different techniques for solving those things. And they are a combination of all the techniques that you can do to compute market equilibrium or to compute like solve the welfare problem. So the first one I just described is when I started this tutorial by describing what is tatonnement. And what I'll do next is describe all the other techniques. All right, so linear programming. The first thing you face, well, mostly when you solve a problem, is try to write a linear program about it. Or rather, try to write integer program and then relax. So a natural formulation of this problem is to write for example, here's a natural formulation. You put some variables xis, which means that agent I acquires a bundle S of goods. And you just want to maximize the value that everyone gets from the system. So maximize the value that I get from S if I get S. So the constraints you need to impose is the first that every buyer needs to get at least one bundle. No buyer should get more than one bundle. The second condition is that every item needs to be sold only once. So for every item j, the set of buyers and the set of bundles containing S, xis should sum to 1. And xis should be integral. All right, so that's exactly the welfare problem. I just rephrase it. It's very easy to see. But I don't know how to solve IPs, you know how to solve LP. So you relax to 0, 1. And as usual in linear programming, you can write a dual. That's what you get. One interesting thing is that the LP is an auth. So for graph substitutes, this integer programming will be integral. Sorry, this integer programming is always integral. This LP should be, the linear programming is integral. So let me show you that the proof is actually simple and it's nice. So the value of the IP is always, the IP is more constrained. So the value should be smaller equal than the value of the LP. So the LP, you have less constraints, you should be able to go further. So the value of the IP is definitely smaller than the value of the LP. And the value of the LP is equal to the value of the dual, that's strong duality for linear programming.
In the objective functions for the primal, are you also summing over S, or is S fixed?
Ah, you're right. No, I'm summing over S. Yeah, it's summing over I and S. Yeah, that's a good point. Thanks for catching that. Yeah, so we're summing over I and S. Right. So now let's try to show it's the value of the IP is equal to the value of the LP. So this is a bound in one direction. So I showed that the value of the IP is smaller equal to the value of the LP, it's equal to the value of the dual LP. That's just strong duality for linear programming. Now let me try to prove the reverse. And to prove the reverse, I use Walrasian equilibrium. So it's Gross substitute, so you know Walrasian equilibrium exists. So take a Walrasian equilibrium, and you know now that Walrasian equilibrium is optimal. It's an optimal allocation. So this allocation that's the allocation that is a Walrasian equilibrium is a solution to the IP. And you know that if it's a Walrasian equilibrium, there's Walrasian prices as well. So P is a set of Walrasian prices. And let U be the utility of the agents. So it's the value of what they get minus the price in equilibrium. Then you have a solution to the dual. Because you can actually, so the first the welfare of the optimal allocation is equal to the value of the optimal IP. That's just a definition. Now if you get the prices in equilibrium and the utility of the agents and plug to the dual, you see that it's a feasible solution to the dual. Right? Because just the utility of every agent is equal to the value minus price for every bundle, because they are getting the optimal bundle. And what you get there is the total value they are getting. That's the value of the, so that, and the LP is a minimization problem. So you can do better. I'm not saying that I'm saying that it's a feasible solution to the IP. So the IP is at least as good as that. So in pretty much the dual LP is smaller equal than the optimal IP, which is equal to the equilibrium. So if you put this and this together, you got the IP is equal to the LP. So that's nice because now you can just solve the LP and you get the optimal solution. Good. Can you solve the LP? Oh, so I'm just saying that also what I said actually here, the theorem that I just proved is actually a little more general than Gross substitutes. If for any set of evaluations you want to see if Walrasian equilibrium exists, it exists if and only if the linear program is integral, if the LP is equal to the IP. I did one direction, but the other direction is just reversing what I said. Can you solve it? So the primal has exponentially many variables. In those cases, usually it's simpler to deal with small number of variables, many constraints. So you can solve by the dual. You can try to solve the dual. That's maybe the usual technique of solving linear programs have decided. You just go to the primal dual that have a small number of variables, large number of constraints, and try to find a separation oracle. So the separation oracle is given a pair of, like for the dual, for example, utilities and prices. Either figure out that all constraints are satisfied for this UI, P, J, or find a constraint that's not satisfied and return it. And the separation problem for the dual is exactly the demand oracle problem. So for every agent I, you can try to, under those prices, find the optimal set of bundle for this agent. If that's greater than the utility, then it's true for every bundle. Then it should hold for every bundle. If it's not, then that's for the one that he likes most, that's the most violating one. So it's nice that you know how to solve this problem, because that's just running the grid algorithm. So the grid algorithm is a separation oracle for the dual. You can solve the dual problem. At this point, you know how to find the value of the optimal. You know how to say what's the welfare of the optimal solution. You don't know what's the allocation yet, because you know really what's the value. You don't know what's the value. You don't know what the allocation is that generates this value, but you at least can know the value, which is a nice thing. And the proof was easy. I just gave an entire proof. There's nothing more than that. Just solving the LP. And in particular, it's saying that if one nice consequence of that if there is Walrasian equilibrium, and if you can actually solve the demand oracle problem in polylemma time, you can separate the dual, and you can find the value of the optimal welfare problem in polylemma time. And one very nice consequence is something that Inbal and Tim Rothgarden proved, which you can use actually complexity theory to show non-existence of equilibrium. So if somehow these problems, the demand oracle and the welfare problem, are not in the same complexity class, then Walrasian equilibrium should not exist. So Inbal is talking more about that in the second part of the talk. So, but I thought it was a very nice connection between using complexity to say things about equilibrium, say something that's not really nothing to do with complexity, they prove using complexity theory as a tool. Right, so it's an LP solution. Yeah.
So to be an anything extra, the polytope is actually integral. That polytope of P is divided
the polytope of feasible allocations.
Like for example, in the special case of the matching,
Mm-hmm.
it's not that easy to got the polytope is actually
You're saying posing. Yeah. So this formulation, the the set of constraints is the set of constraints is fixed. I'm just changing the objective function. But you're saying you can find another formulation that makes that would be a nice thing to do. Yeah. I think you probably can get nice theorems from that too. But yeah, it should be possible to prove some of those theorems in like properties of like putting structure in the constraints instead of putting structure in the objective function. Yeah, so I think it would be a nice direction too. So here I'm going next is actually the opposite of what you're asking. I'm pushing everything to the objective function, including the constraints, which is one technique in convex optimization is that if you have constraints are less nice to work with. Let's just push them to the objective function by Lagrangiifying them. So whenever you had UI, you can just put a maximum VIS minus P of S. So you can describe this called market potential. And this function will be convex because it's just like everything. The last function is linear, just sum of PJs, the linear function. And this is the sum of maximum of linear functions. So everything the VIS minus PS is a linear function. The maximum of linear functions is convex. So you have this this function here. And one thing that comes out of the previous analysis is a set of Eurasian prices are the minimizers of phi, whenever Eurasian price exists. So phi usually will have minimizers. But if there is any Eurasian price, it will be the set of minimizers of phi. And then you have in that point, you're on the situation that make people in convex analysis very happy. They have the things they're trying to find is a minimum of a convex function. We know how to minimize convex functions, just run gradient descent. Let's look at what gradients say. So that's the gradient of this potential. So the function is to find a set of prices. So you take the gradient, the derivative of phi. Now it's usual derivative, not discrete derivative. It's actually a normal real analysis derivative with respect to the price of item j. It's easy to do if you see in the envelope theorem. It's just an application of the envelope theorem. When you take the derivative of a maximum of linear functions, you first find the function that realizes the maximum and take the derivative of that function. So the derivative of the potential will be 1. 1 is the derivative of sum of pj's, minus for every I, that's if j is in the set of demanded items for I. So let's say demanded items are unique. If they're not unique, it's a subgradient. But let's forget it for a second. Let's say that there's one minimizer for every S. That's so 1 minus sum of I, sum of all buyers, if j is in the favorite set of agent I. So that's very nice because gradient descent is saying something very intuitive. So gradient descent says that if you have some price, you should move in the direction that's opposite of the gradient, so in the direction of minus gradient to minimize. And it's saying that you should increase the price if the sets are over-demanded. So if the sets are over-demanded, this sum is more than 1, and which means the gradient is negative. But now we move in the direction of minus gradient, so you should increase the price. And if items are in the opposite, if items are under-demanded, sorry, I wrote over-demanded twice. Yeah, so here should be under. So if the items are under-demanded, this thing should be 0. So the gradient is 1, so you should decrease the price. That's pretty much the intuition that Walras had, that you should increase the price of things that are over-demanded, decrease the price of things that are under-demanded. So the intuition of the intuition that Walras had is really just saying you run gradient descent. Good. Yeah, they have a good question. So in that case, the gradient is not well defined. You need to you need to take a subgradient. So everything here will be a subgradient of the set. Any subgradient works. Yeah, you can move in the direction of any subgradient. You can pick demands of however you want and just run. That would be the method that people call like subgradient descent. So the function is it's not smooth. So there's not one gradient for every When it's a gradient, you can just pick go the direction of any subgradient. Yeah, and the nice thing is that tatonnement is a form of gradient, or gradient descent. So tatonnement is saying it's a funny way of doing gradient descent, but but in some sense it's just saying figure out the sign of the gradient and move the prices epsilon in the direction of the sign of the subgradient, or the gradient of the subgradient. So in some sense, the analysis that I just described of tatonnement, one alternative analysis, if you want to just say what I describe is a Kelson-Crawford analysis, but maybe if you could come up with a modern analysis, you could come up with a potential function and just use the analysis of gradient descent and give analysis of tatonnement. So that's gradient descent. So let me tell you some methods. I will compare some methods for, I'll compare the methods that I described so far and the methods that I will still describe next. I'll mention in two different ways, oracle, access, and running time. So when you compare the different methods, you might ask, sorry, yeah.
Getting back to the slide. So if you had like specific valuation functions, could you do things like use the KKT conditions to algebraically characterize the?
Probably yes. That's a good point. Yes, you could do that. If you have a closed form formula, you could use things like KKT conditions. And what you see next, also you can use other things like cutting plane methods. You can use them pretty much like this. This setup will allow you to use probably any convex optimization method that you're used to. You could apply in this formulation. It's very general. So maybe actually the next thing could relate to your question. Actually, when can you apply KKT conditions and you cannot? So the next method means like what's the access that you have to the valuation functions. If we talk about computation, these valuation functions are like combinatorial set functions. So they are like 2 to the n values for every buyer. So usually you have something that has a very high cardinality. You usually don't imagine you have a table written. You imagine you can access it through an oracle. So there is 3 natural oracles, and this is how close you actually look into the market. So if you look at the market very closely, so for every buyer, you can actually look in the heart of the buyer and say, what's your value for this bundle of goods? So for every buyer, I can query, tell me how much you like this pair of grapes and apple and oranges. So it's a value oracle. That's a nice thing to write theorems. It's a bit unnatural that you can actually, I mean, maybe in some situations you can. It's good to know what you can do with value oracles, but value oracles is some less common thing to have access to in practice. Demand oracle is something slightly more common. There's prices out there in the market, and then for every buyer, they come to a supermarket, the items have prices, you see whatever they purchased. So you can ask for each buyer, given some whatever your valuation is for those prices, which give me one of your favorite bundles. That's one way to access the market. And it's also just like if you look at the market from very far, you look at the entire city of Ithaca, you really don't know it's very unlikely that you can ask for each person how much they value each item. You can ask for the entire market. In your supermarket, you can actually set prices for some goods and figure out the entire demand over the population. So the sum of all goods demanded. You can like set prices, all the population of buyers or your population of Ithaca will come to the market, they will buy some stuff, and you figure out the total amount that was bought and total amount that wasn't bought. So it's aggregated demand. Here I don't even have access to who are the buyers, there is any buyer. I don't even know the identity of the buyers, I just know in aggregate what they want. The nice thing about tatonnement and gradient descent is that they really need this very general aggregate demand oracle. So they don't need to know how many buyers there are in the market. So run gradient descent at tatonnement, they just need to know what's the total aggregate demand over the market, not the individual demands. I don't even need to know how many buyers or anything or any identity of the buyers. But the problem is that they run in pseudo-polynomial time. There's linear program approach, and also the KKT conditions I think also fall in this category. That you actually you access the value. You need the demand of every buyer, so you need to run this linear. You need to add constraints for every buyer, and you also need to know the value they have for the goods. But the nice thing is that now it runs in weekly polynomial time. So there is a way to get also both things. There is a way to get actually to aggregate demand oracle in weekly polynomial time using cutting plane algorithms. So you use convex optimization formulation, and then you try to run a cutting plane. There is some tricks here because in cutting plane algorithms you usually know how to evaluate the function. This is an interesting convex optimization problem that you know how to evaluate gradients, but you don't know how to evaluate the function. So you don't know how much is phi, but you know what's the gradient of phi. One thing that I thought was interesting is actually you don't need that many calls to disaggregate the demand oracle. You just need like number of items call us to disaggregate the demand oracle to find a set of origin prices. And but it's still a weakly poly, so I like to do like maybe strongly poly. And what I will do next is spend like maybe the rest of how many minutes I have. Oh, I do have actually half an hour, so less than that actually, probably the next 15 minutes or so. Describing combinatorial algorithms. I'll give some strongly polynomial time algorithms for this problem. And that's the two Murata. I'll show how to compute for gross substitutes and exact equilibrium in that much time, mn plus n cubed. M is the number of buyers, n is the number of items, and TV is oracle calls. So time we need to call the value oracle. Okay, good. So I think at this point, or can we jump to combinatorial algorithms? All right. I like because this combinatorial algorithms, like a lot of things come together, like network flows, shortest paths. They all are a lot of interesting things, a lot of interesting techniques get here. So I'll start by this problem. Given optimal partition, find variation price that support this partition. The nice thing, okay, so the setup is I give you some partition of the items, and I ask you, please find a set of variation prices such that the set Si is demanded under those items. And the nice thing about gross substitutes that to check, remember that gross substitutes is equivalent to discrete concavity. So the only thing to check, if I don't want to remove, to check that Si is optimal, is that I don't want to remove an item, I don't want to add an item, I don't want to swap an item that I have for an item that I currently don't have. So here's a clever way that Murata found of solving this problem. He will build the following graph. These are the items, every item there is, and I'll put a circle saying who these items belong to. I'll put an extra node in each graph, which is a dummy item, saying that's an empty space, let's say. I'll show you what the empty space is very soon. And I'll create the following edges. For j to k, that's a difference in value if this agent that say S1 or say agent I drops agent j and replaced by item k. So how much he will lose if he did this swap. The same way I use for dummy item, from the dummy to k, is how much he will lose by actually adding k, or win or adding k. Similarly from j to phi, how much what's the difference by dropping j. And between two dummy items, I'll just put an edge of 0. Good. So for every item, I add edges for every other, everything else that I don't own. So everything else outside my circle. I do that for every. I did that for every item to be a bunch of arrows. But I have a graph. And one thing you can do is you can compute shortest path in this graph. So you can compute shortest path from. So one thing to note is that all the phi's are connected to each other by edges of weight 0. So I had the phi's. All the phi's. All the phi's are connected to each other by an edges of length 0. So all the phi's are pretty much the same node, right? So there is nothing from the. I can imagine they're the same node. They're just like there's distance 0 from every phi to every phi. So I can ask what's the distance from phi to every other node. Okay, so that's the distance function. So distance functions not always exist. The reason distance function exists if there's no negative cycles. If there's no negative cycles, you can run Bellman forward, or you can, and you can get like distance function. So let me take this theorem and I'll give a proof. So if the allocation is optimal, the exchange graph has no negative cycle, and I can find the version prices. If the allocation is not optimal, you find the negative cycle. So the proof goes this way. If there's no negative cycles, the distance was well defined. I can define distance from the dummy nodes to every other node. I set the price as minus of the potential, minus of the distance function. And the distance function will be, it's a distance. So it will have, it satisfies the triangle inequality. So you have like that's the whole definition of distance function. The distance from phi to k is more like a distance from phi to j plus the edge from j to k. And if we write this, this expression by substituting distance by minus pi j and wjk by what it actually is, as a differential wkj, you say that you arrive at something that says that the buyer I for the current Si prefers Si to adding k and paying for k and dropping j and getting back what he's paying for j. Which means that if there is a distance function and the prices are minus the distance, it means that buyers don't want to swap any item they have for the item they don't have. If you do the same exercise of substituting it for the other edges from the dummy items for every other one, you see they also don't want to acquire and remove an item. So pretty much you have a potential, and there's no negative cycles. It's saying that Si is locally optimal. But again, you saw that this is gross is equivalent to discrete concavity. So local optimality is global optimality. So it means that is a global optimal. That's global optimal. And Pj is a version price by the differential version prices. So it's good. We are happy, and then conversely, version prices. So I prove one direction. There's no negative cycles. The exchange is optimal, and I can find version prices. And the opposite is also true just by replaying the proof in reverse. If there is, if there are version prices, I can find, I can define a distance function. If there exists a distance function, there's no negative cycles. And then just read the proof backwards. It works. And there is actually a very nice consequence from that. Actually, I thought that's pretty cool. Actually, this is because I've seen the proof of that fact before, and they always like it's a very easy proof that version prices from a lattice. Lattice means that if you have two sets of version prices, if you take the component-wise minimum, there's your version prices. If you take the component-wise maximum, there's your version prices. And that's just by the fact that potential functions from a lattice. And that's very simple to see. If you take two distance functions, d1 and d2, you can just do the case analysis and see that the minimum of d1 and d2 is still a potential function. And the maximum of d1 and d2 is still a potential function. So potential functions from a lattice, version price is nothing more than potential function on a certain, the potential, I mean distance functions on a certain graph. So version price is also from a lattice, which is a nice thing. I think Inbal is going to use that in the part of the talk. Actually, show you nice economic properties come out of that, of this lattice structure. All right. Second problem is also easy. Like now it comes actually as a simple corollary. If I give you a partition, verify that's optimal, that's simple. Just like try to build a graph, try to see if there is any negative cycles. If negative cycles, this is not optimal. If there is no negative cycles, then it's optimal because you can find version prices. Okay, good. So let's try to find the optimal then. That's what we are left to do. And Renato has a really clever solution for this problem. And it has actually a couple of different algorithms through time, but that's, I think, what's the cleanest one. Which is he wants to, the way he proposes to solve this problem incrementally. So for every, he adds the items one by one. So the version equilibrium problem is one item is very simple. Just look at who wants to pay more for this item, give to that person. That's at that price they want to pay. That's the trivial solution. So let me just put in the items in any order. I put one item, and I compute a set of version prices for that one item. So that's the problem W1. And then I'll keep adding item by item, and then compute the optimal allocation for the set of T items. All right, so problem W1 is easy. Now let's assume we know how to compute WT for, so the optimal location of items 1 to T to the M bias, and I have a certificate. And also assume that the certificate is maximal. So I know the version prices from a lattice, and I'll take the maximal one. I'll tell you an algorithm that if you start the set of version prices, I'll add a new item, I'll give you an optimal location for 1 to T, and I get also the set update to get a maximal set of version prices for those items. Right, so I'll build an exchange graph the same way that I did it before. And the exchange graph just is the first T items, let's say. I have only, let's say, T items already solved. I have a set of version prices. I build exchange graph like before, the same edges I add, the same edge weights is a little different. So I add the prices also to the edge weights. There's a common technique in flow problems that you keep finding potentials and add the potentials to the edge weights to make the computation faster. So the nice thing is that given that this piece are variation, all those edges are non-negative. So I have now I could change the potentials that every edge is a non-negative. Every edge is greater than 0. So nice. Now I need to update this allocation to add this item T plus 1. So T plus 1, right now I don't know who owns it, so let me just put it outside. And I add an edge for between every buy and every item to T plus 1. So the weights of the edges will be the natural weights you can imagine, like the edge from, for example, this the dummy item to T plus 1 is what's the cost of him adding T plus 1, what's the difference in value he get by adding T plus 1. And the edge from this item to T plus 1 is what's the difference in value this buyer will get by swapping, by dropping this item and acquiring T plus 1 instead, right? I mentioned also the dummy items, they all have edges 0 between each other, so let me just add a meta dummy item and connect to all of them. It's good. And what I'll do is just compute shortest paths. So the shortest path from the dummy item to T plus 1, let's say that's the shortest path. So the algorithm will just like take the advice of what the shortest path is doing. Actually, so maybe we should have said something. You need actually if there is a single shortest path, you should use the shortest path. That's actually missing the slides. If there is more than one shortest path, you should take the minimal length shortest path. And that's easy to compute also. You can just like, it's a simple exercise. You can modify Dijkstra's algorithm to, if there's more than one shortest path, you just output the minimal length among all the shortest paths. So the minimal length among the paths that have a minimum weight. Right, but let's say you have such a path, it's very easy to compute using Dijkstra, or slightly modification of Dijkstra. And then take the advice of what this path is telling you. This path is saying the buyer 1 wants to should better acquire this item. The buyer 2 would rather drop this item and acquire this other item. Buyer 3 should rather drop this item and swap for that item, and so on and so forth. And eventually, and buyer the 3 would like to swap that item by T plus 1. So you perform all the swaps that they indicated by the arrows. So those are the arrows. They're indicated by the arrows, and then you get now T plus 1 is allocated. In the theorems that this allocation is optimal. Also, actually, okay. So the next slide is how the allocation is optimal. We just want to say that that's the algorithm. How do you compute the optimal allocation? And the nice thing is that this graph has only non-negative edges. So that's how much it took to compute. Dijkstra takes some interest tilde here. You also take pay some logs for the nodes also, but that's pretty much how the running time is. And if you do any iterations, we get actually that running time. You get an extra square here, but you can remove that if you're a little more clever about this construction. But that's easy how to remove the square. You just think a little bit. You can actually reuse computation a little bit between 2 iterations, and but the idea is pretty much like all the interesting parts are here. So the proof is the following. After you did the swaps prescribed by the optimal by the optimal path, then you end up with a new set of allocations S1 tilde to Sm tilde. And you can define a new set of potentials based on the new paths. Okay, Pj tilde. The proof goes into steps. The first is show that the new prices are also a certificate for both the new and the old allocation. So the allocation of the T first items, it's supported both by the old and the new, for both P and P tilde. So that's an easy step. It just follows from analyzing its duality for shortest paths. The second part is actually the tricky part, which I actually won't give you the full proof, but I'll just tell you one case in which that's easy to see. Under the new set of prices, every buyer is indifferent between the old and the new allocation. He doesn't care if you get the S or SI or SI tilde. Which is nice, because if they don't care, that means that an SI is optimal, then SI tilde will also be optimal. And that to be the full proof. So let me just tell a word about item 2, part 2. Item 1, I just said it. If you just look at the duality for shortest path, you get that. I just write shortest path linear program, look at the dual. That's what you get. Part 2, it's simple. If you are, for example, buyer 1, there is only one edge entering, one edge leaving. So that's very simple. That under these prices, under the potential, the new prices, all the weights of new edges become 0. So it means that under the new prices is indifference between between using this edge or not using this edge. If for every buyer, for every big circle, there is only one edge going in, one edge going out, that's the full proof. The problems that maybe by buyer 2, you might have two edges going in, two edges going out, or more than one edge going in, more than an edge going out. His difference in value might not be the sum of the edges going in or going out. And that's where the fact that you need to take the minimal length shortest path comes into picture. If you take the minimal length shortest path, you can actually show that for that thing, the sum of edges going in and going out is the number of edges crossing the border is really the difference in value. And that there is actually a nice, that I found this, I find this proof very nice. It's a very clever combinatorial proof that Murata has. But I won't go over the details, but I can point to where you can read that. So item 2 is, there is just showing you where in the proof there is a nice magic going on. So this second statement. All right, so that's one more thing before I conclude. I show you so far. I showed you so far some various different definitions of graph substitutes. I showed you the equivalent that gives us some tools to design algorithms for them. I show how to combine them to design different algorithms. And in the end, I'll just talk about some nice open problem that I really like about graph substitutes. And it's about the construction problem for graph substitutes. So you can ask, like, if you have graph substitutes, how do you define how do you construct functions from other functions? If you have two functions of graph substitutes, the sum of them might not be graph substitutes, which is a bit funny. Like most classes, like submodular, subadditive, they are close and at least like linear combination, convex combination. No, graph substitutes are not. So the geometry is a bit more strange than other classes, but they have actually nice properties that preserve some operations that preserve substitutability. One of them is affine transformations, like summing to a linear function plus some constant does preserve. And that's a simple thing. That's just from the fact that that the whole definition of substitutability is a property of the second order derivatives. So if you do a linear transform, if you do sum a linear function or sum a constant, that won't change. You should change maybe the zero order and the first order derivative, but won't change the second order derivatives. So affine transformations should be fine. Endowment is fine. Endowment is this word comes from economists. They say that if you give them some goods, the marginal valuation for the remaining goods is your substitutes. It's nice, and also there's this property called convolution. You say the convolution of two valuations is the maximum you get from partitioning those items into a subset for buyer 1 and subset for buyer 2. So that's the maximum, the best value of the partition that goes from 1 and 2. And it's an interesting, maybe exercise to try to prove the convolutions are close. You can try to reason about the analysis that of Walrasian equilibrium of the tatonnement. It comes out of the analysis. It's not a very hard proof, but it's an interesting fact. Hey, right.
So why do you call it convolution?
Convolution because when you do so when you call the way that I view convolution of two functions, kind of the integral of f of x, integral of g of y minus x, let's say. This is really, instead of integral, let's say you replace by a maximum operator, and you think that's the v1 plus v2 of x is equal to this operator over the sum of like v1 of x, v2 of y minus x. There's some
The integral is not the product.
exactly. But it's a general kind of thing. I think you can define convolution more in general sense. That yeah, so like given an operator, given some operation in between, it's pretty much how to. Convolution is like partitioning the sink into sinks and take some operator over them. That's kind of the literature people call this convolution. That's I think it makes sense. A nice name. Some other I think there's also Lema Nielsen called this the OR operator. That's also another name that was being given to this operation. Yeah. And finally, there's other properties that such that preserve substitutability. This thing called strong quotient sum, true concordant sum. I won't define them, but I'll end up with an add. And the add is that actually an open question and then some add that you should see one talk in EC. So one open question is how do you construct gross substitutes for matrix rank functions? Let's say you start with all matrix rank functions, and you're allowed to apply any of those operations. You're allowed to stitch to matrix rank functions by, like, I don't know, doing affine transformations, endowments, convolutions, true concordant sums, strong quotient sums, and other operations. Can you construct all gross substitutes? And that's not known. So there is a subclass of substitutes called matroid-based valuations, which will start with matrix rank functions, and you apply convolutions, the first three operations, convolutions, endowments, and affine transformations, and you can ask, like, is that enough? We don't know. That's open. I really like these questions. They're my favorite questions. There is some paper by Eric Balkansky and myself in EC on Thursday that makes some progress, but it makes progress in showing that there is a negative answer, that some subset of these operations cannot construct all substitutes. So if you should be interested to come to Eric's talk on Thursday. So now I think that's all I had to say. It's the end of part 1, and in some minutes, I don't know when, we'll the date, Inbal is talking about economics and also pushing the boundaries, how to go beyond substitutability and carry some of those properties to more general class evaluation functions. Thank you, and if you have any questions. So if not, what time do you come back, actually? 4? Okay, so 4, you have now we have actually 40 minutes break, so you can take, yeah, thank you.
Okay, I'm gonna start more or less now. Okay. Okay, so welcome to the second part of the tutorial. Can everybody hear me? Okay, so let me give you an overview of where we are. We've discussed, we've already discussed combinatorial and algorithmic properties of GS, gross substitutes. And now what I want to do in this part is talk about economic properties and then pushing the boundaries of GS. So to remind you what we saw in the first part, so we saw that GS has some remarkable combinatorial and algorithmic properties. We saw that for a single GS valuation, we have some exchange properties, and we have optimality of greedy and also local search algorithms for solving the demand problem. And then for multiple GS valuations, or in other words, a market, we have Walrasian market equilibrium existence. And we also have that the problem of welfare maximization is computationally tractable. So by the way, I think it's sometimes confusing. When do we refer to just a single GS function, and when are we talking about a market or a collection of GS functions? So I'm trying to use these pictures throughout the slides. OK, so what are we going to see in this part? So first of all, we'll talk about economic implications. I'm going to show you several central results in market design that depend on these nice properties of GS that we saw in the first part. And this will be based on classic theory and also some recent insights. And then I'm going to talk in the last half hour about pushing the boundaries of GS. So we have all these nice properties. Are they confined to GS, or can we extend the boundaries a little bit and get them to hold more generally? And just a disclaimer, the literature is huge, so it's too big to survey comprehensively. So just think about this as starting point to the existing literature. OK, so before I dive into the technical details, I want to give you a little bit of motivation. So as I mentioned, there are several fundamental market design results related to indivisible items that rely on the GS assumption. And the ones I'm going to present to you today are the following. First of all, that equilibrium prices exist. We saw this in the first part. They have a nice lattice structure. And then we were going to talk about VCG and how when the valuations are gross substitutes, how it has really nice properties. And then the invisible hand of the market works really well in terms of prices coordinating the individual actions when we have GS markets, or more accurately, typical GS markets. This nice property that GS is preserved under economically important transformations Renato mentioned in the first part. And then I hope I'll have time to get to some interesting connections between the economic and algorithmic properties. So one more slide of motivation. So we have this huge literature, as I was saying, about gross substitute. But I want to claim that in some sense, in this community, it's a little bit of uncharted territory. So we always have this picture of hierarchy of valuations. And we've studied submodular and subadditive so much. And we've even gone beyond submodular and subadditive. So we've looked at pushing the boundaries of submodular, pushing the boundaries of subadditive. We have this nice hierarchy results that apply there. But for gross substitutes, we really don't know a lot. I'll tell you in the last half hour what we know. And you can kind of, if you're looking for open problems to work on, I think this is a great one. OK, so that was the motivation. Now I want to remind you of our model. So here's our market model. We have M buyers M. Sorry for those who are used to using N for the number of buyers. We're following a survey of Renato. And then I'm going to use notation G for the grand coalition, by which I mean the M buyers plus the seller. So player 0 is going to be the seller. I have indivisible items, N of these items. And an allocation is just a partition of these into bundles. I'm going to denote it by S. And the bundles go to the different players. And then I have prices. I'm going to use P for a price vector. And I'm using the notation of P of a bundle S to denote just a sum of the prices over the individual items. So immediately, P of all of the items together. This is going to be the seller's utility, or in other words, the revenue, if he sells every one of the items that has a non-zero price. In other words, if the market clears. OK? So this is the market model. And just to remind you, if we kind of zoom into one buyer, here's the model. So a buyer has a valuation, which is a function from bundles of items to a value. This is what's going to be gross substitutes, usually, in the discussion. If we fix item prices P, the vector of item prices, then if the buyer gets a bundle Si, she has quasi-linear utility, meaning that I'm denoting this by pi I. I think maybe the notation in the first part was a little different. It's just the value of her value for the bundle minus whatever she has to pay for the bundle. And we say that a bundle is in the buyer's demand if given the vector of prices, it maximizes the utility that the buyer can get. So he looks at the prices, looks at the items, picks the bundle that maximizes her utility. Okay. Great. So that was the model. Any questions about this so far? Okay, so I want to start with a few preliminaries that I'm going to use later to show you the fundamental market design results that rely on GS. And the ones I want to talk about are the core, remind you what a core is, talk about lattices and, talk about lattices and what does it mean to be some modular on lattices, and then present the differential dual. Okay, so starting with the core, let's consider some cooperative game, which is defined by a set of players, G, and something called the coalitional value function, W. And so I've drawn a game here, and we can see that these two players together, they can join forces and get value of 6. And all these three players can join forces and get a value of 8. Now, every outcome of the game has a utility profile, a vector of utilities. For example, here, maybe the first player gets 2, 3, and 3 for the 3 players. Now notice that this outcome vector, it's not very good. This utility vector, it's not very good. Why? Well, it's going to be blocked by a coalition. So these 2 players here, together they can create a value of 6. But their outcome together is only 5. So they prefer to kind of, go on their own and create the value of 6 and divide it in some way between each other, and then they're happier. So we say that this utility profile is in the core if there's no blocking coalition. So if this thing doesn't happen. Or in other words, if going over every possible coalition, you sum up over the utilities, and that's more than the value function, the value that they can create. Okay, that was the core. Now lattices. So a lattice is a partially ordered set of elements in which I can take every 2 elements, I can join them, or I can meet them. And the result is also within the set of elements. So by join, I mean you take the smallest element that upper bounds both. By meet, I mean you take the largest element that is lower bounding both. Let's see a few examples. So the first example is taking all subsets of an item set n together with just looking at 2 sets and seeing whether they contain one another. And so if you have 2 sets, their join is just their union, their meet is their intersection, and both of these are within the original set. Okay, another example, vectors in Rn. So here, let's say I have 2 vectors s and t. I can take their component-wise maximum, and this will be their join. I can take their component, and this is this vector. I can take their component-wise minimum, this vector, and both of these will be also vectors in Rn. Okay, so that was 2 examples of lattices. And notice that it's really natural to define the product lattice, right? If you have a pair, let's say, for example, a product lattice between the n-dimensional vectors and subsets of players, coalitions. So you have this pair, and you have another pair, and you want to join them. So you join the 2 pairs the 2 pairs separately, and you can meet the 2 pairs separately. So that's a really natural definition. Okay. And now to remind you what submodularity looks like on a lattice. So so a function f is submodular on the lattice if this familiar inequality holds. The only thing to notice is that I used here the join and the meet instead of usual maybe set union and set intersection. Okay, last piece of preliminaries, the differential dual. So here notice that I'm talking about just a single valuation, and for this I'm defining its differential dual. Let V be the valuation. Its differential dual, I'm going to denote it by U. And it's a mapping from prices. So it takes a vector of prices, and it returns the buyer's maximum utility under these prices, if this buyer has the valuation V. So it's just it's an equivalent way of asking a buyer what's its valuation. Instead of the valuation function V, where you come to the buyer and you say, oh, here's a bundle of items, what's your value for it? If you're using the differential dual as the representation, you come to the buyer, you say, here's a vector of prices. Please tell me what is the maximum utility you can get from this vector of prices. Okay, so it's an equivalent way. Now, the same way that we could define growth substitutes on valuations, we can define growth substitutes on utilities, on differential dual. This is, by this theorem of Ausubel and Milgram, a valuation is growth substitutes if and only if its differential dual is submodular. Okay, so sometimes this is called the convex conjugate. It has some other names, but we'll refer to it as the differential dual. Okay, I did want to say a few facts about the differential dual. So notice that in the first part, we had this duality between maximizing welfare subject to feasibility of the allocation and minimizing the total utility. Actually, if you can notice that this thing we're minimizing here, it's sum of utilities of the individual buyers plus this utility of the seller, right? The revenue, the sum of all the prices of the seller given P, subject to buyers maximizing their utility. And I want to show you how you can rewrite this using the differential dual, and this is going to be really useful in what follows. So let's rewrite this. So now the minimization is just over P. Before it was over the utilities and P. Now it's just over P, and I'm using the differential dual, which it has this buyers maximizing their utility built in. Okay, and last thing I want to say about the differential dual is why is it a dual? So I've copied what we saw on the previous slide, and we know that for GS we have integrality gap of 1 of the configuration LP. So welfare maximization is exactly this what we had on the previous slide, minimizing over the prices. And now notice that this holds for any market. So you can apply it to just like say to any coalition of buyers, you can apply it to a single buyer and any subset of the items. So if you apply it to buyer I and bundle S, then we get the duality. We get the valuation of the buyer for the value of the buyer for a bundle S is exactly minimum over all price vectors of the differential dual plus the revenue. So this is the duality result and why it's called the differential dual. Okay, so this is the preliminaries. Any questions so far? Okay, so now I want to use the preliminaries that we just went over to show you economic implications of GS. And the ones I want to go over are the equilibrium, the lattice structure of equilibrium prices, VCG, and then prices coordinating typical markets. So let's start with the first one. Okay, so we're talking about the equilibrium prices. Remember that this is what the equilibrium looks like. It's a pair of allocation and prices, such that for every one of the buyers, given the prices, they're allocated something in their demand, and that the market clears. So now let capital P be all the equilibrium prices, and a theorem by Gould and Stacchetti tells us that these prices form a complete lattice, meaning that, first of all, if I have two price vectors, P and P prime, if I take their join and their meet, they're also equilibrium prices. And it's a complete lattice because if I look at the component-wise supermem of all of the prices, and if I take the component-wise infimum of all of the prices, both of these exist and are also equilibrium prices. So I have maximum prices that are in equilibrium prices and minimum. And these have a really interesting economic characterization. So here's another theorem by Gould and Stacchetti. In GS markets, the highest price of an item over all the equilibrium prices is precisely the decrease in the welfare if you take away this item from the market. And the lowest price, the lowest equilibrium price for an item is precisely the increase in the welfare if you add another copy of this item to the market. Let me show you an example. So here's a market. I have two items, and I have two buyers. So this buyer is just interested in the pineapple. This one, let's say, is additive over both of these items, and these are their values. And you can see that the maximum welfare is achieved by this bold allocation here, and the welfare is 5. So let's take a look at the equilibrium prices. On the x-axis here, I have the price for the strawberry. On the y-axis, I have the price for the pineapple. And let's start by looking at two equilibrium prices, P prime and P. So you can check that they're equilibrium prices. For example, if we focus on P, then you can see that this buyer is happy because she gets the strawberry, and she doesn't mind not getting the pineapple because the price is 2 and her value is 2. And then this buyer here is also happy because he only wants the pineapple, and he's getting the pineapple, and the price is below his value, and so everything is good. And same way you can check P prime. Okay? And now, as we saw from the theorem of Coulomb-Stucchetti, their join and their meet are also both equilibrium prices. You can check this. And moreover, they have this economic characterization that we saw before. So I've written here the welfares. If you take away the pineapple, you take away the strawberry. And here, with an extra pineapple and an extra strawberry, well, you can check that this price vector here, 2 and 3, is exactly the difference if you take away the pineapple in the welfare, so it's a difference of 3. And if you take away the strawberry, it's a difference of 2. So the theorem checks out in this this example. This is just to demonstrate the theorem, so it doesn't. So it's more. You have a mental picture. Okay. Great. So an immediate corollary of this, if you're wondering why is this useful, so here's just one corollary. So you can see that in unit demand markets, the lowest prices coincide with VCG prices. I won't really go over this, but just it kind of makes sense, right? So the lowest prices is what you would get if you add an extra unit, and the VCG prices, well, what somebody has to pay is their externality on the other buyers. So it kind of sounds like the same thing, and it is the same thing. Okay, so that's all I wanted to say about equilibrium prices and their nice structure. Now I want to move on to two other economic implications, and here I'll show you proof sketches. So let's start with the first one. And this one is about VCG. So by the way, any questions about the lattice structure? Okay, so VCG, to remind you, is a multi-item generalization of second price Vickery auction. It's the only dominant strategy, truthful welfare maximizing auction in which losers don't pay, and this means that theoretically it's really important. And the question is, but is it practical? This turns out to depend on its economic properties. So to analyze these, let's define the coalitional value function W. Okay, so here's a definition. W maps coalitions of players from the grand coalition to the maximum welfare that can be obtained from taking this set of players, taking the items that they own, and reallocating the items among them. So clearly, first of all, if the seller is not part of the coalition, then the coalitional value function is going to be 0. There are no items. Second, also immediately, if you apply W to the grand coalition, then this is just the maximum social welfare. And also notice that if you have this W defined, then this immediately defines a cooperative game among the players, and we'll get to this in a couple slides. Okay, so now I can rephrase the VCG auction in terms of this coalitional value function. Here's how. Well, the allocation is just the welfare maximizing allocation. This is by definition, it's a welfare maximizing auction. And now for the prices, well, the prices are set precisely such that the utilities of the players are their marginal contribution to the social welfare. Okay, so whatever the grand coalition value is with buyer I compared to what it is when buyer I is taken away. This also gives us the seller utility. Okay, the sum of utilities of all of the players is the welfare. So the seller's utility is the welfare minus all of the marginals that the buyers add to the welfare. Okay. Now VCG can go terribly wrong in in practical sense. And let's see this in an example. So here we have two items. And we have three players. The first player is all or nothing. So she wants both fruit. The two other players are unit demand. So they want either the pineapple or the strawberry, and the values are all 1. Okay, so what does VCG do? Maximizing the welfare here means that this bold allocation is chosen, and the utilities of the players are going to be, there are 4 utilities because I'm also counting the seller. So the first one, the 0 player is a seller, gets 0 utility. 0 utility for the player number 1, and then these two players, well, they contribute 1 each to the social welfare, so this is their utility. So anybody notice something wrong about this this outcome of VCG? Would you be happy if your player is 0 and 1? This is the question. Well, so you wouldn't. Your utilities together are 0, and you can just kind of you can block this outcome and give the first buyer both of the fruit. Then you have welfare of 1, and you can divide it amongst yourselves, and you're happy. So VCG outcome is blocked by a coalition of players. This is not good. It's actually, in practice, comes up. It's not a good outcome. Okay. Second thing that's wrong. Let's see what happens if we take away the third buyer. So if we take away the third buyer, now we have 2 ways of getting maximum welfare. Either player 2 gets one of the fruit, or the first player gets both. So the utilities are now 1, 0, and 0. The utilities of the players are 0 because none of them contribute to the social welfare, because either one of them can create social welfare of 1. That means that the welfare all goes as the utility to the seller. Now, why is this bad? Well, compare it to what we got here. So the seller is actually happier when the market is smaller. And this is really counterintuitive in an economic sense, right? We have more buyers, we have more competition, and the seller loses money. So non-monotone revenue is also a terrible property to have in practice. This means that it's not going to be something that is going to be used as an auction in practice. Okay, so what's really going on here? So what's happening is that buyers choose marginal contribution to the welfare, or this utility here. It's increasing when the coalition includes buyer 3. So another way to say this is that the coalitional value function is not submodular. Okay, so the marginal contribution of one of the players is going up as the set increases. Okay, so it's not submodular. Okay, and it turns out that this is the only thing that can go wrong. So if W is actually submodular, then VCG has great properties, and we'll see that it's submodular exactly if all the valuations are gross substitutes. Okay, so here's more formally what I just said. So if W is a coalitional value function, if pi of C is the utility profile from applying VCG to coalition C, then a theorem by Azabel and Milgram shows equivalence between all of the following. So first of all, for every coalition, the utility profile is in the core, so it's not blocked by any coalition. So the bad example that we said doesn't hold. For every coalition, this outcome is monotone in the buyers. And if the utilities are monotone, this includes the seller's utility, which is the revenue. So it's revenue monotone, so this is good. And these two properties are equivalent to having this coalitional value function be buyer submodular. And buyer submodular just means submodular when restricted to coalitions, including the seller. So for whatever points there are that the function doesn't give you 0, it's a submodular on this. Okay, so I'm not going to show you that theorem. It's the proof is not very complicated. What I do want to show you is what's the connection to gross substitutes. So it turns out by another theorem of Azabel and Milgram that for W to be buyer submodular, for every, let me first say this informally. For W to be submodular, the valuations all have to be gross substitutes. Now, more formally, this is a maximal domain result, like the one that we saw in the first part of the talk for existence of equilibrium. So formally, you take a class of valuations that contains within it additive valuations. Before we had unit demand, now we have additive. And the statement says that for every market with valuations coming from this class, a necessary and sufficient condition for buyer submodularity is that all valuations in the class are gross substitutes. If there's even one valuation that's not gross substitute, I can take additive valuations and create a market in which the buyer, the coalitional value function will not be buyer submodular. Okay, so any questions about the statement? Okay, so I want to do a proof sketch. And this will kind of tie in a lot of the technical definitions we've had so far. So let's start first with sufficiency. So, right, so I want to show you that I'm assuming gross substitutes and I get buyer submodularity. Okay, so remember that we had in the preliminary part that for GS markets, the maximum welfare is equal to this minimization over all price vectors. And we're using here the Differential dual. So we can apply this in particular to any buyer coalition together with the seller because this, the coalitional value function is really, it's exactly the welfare if we restrict the market to this set of players. Okay, so we have some expression for this function that we're trying to show it's submodular. Great. Okay, I copied it onto the next slide. And now let's take this part within the minimization and let's call it f, a function f of the price vector in the coalition. And now, since the Differential duals are submodular because we're working with gross substitutes, then this function f here is also going to be submodular on the product lattice of prices and coalitions. And we can apply a result by Topkis that shows that if you have a submodular function on a product lattice and you minimize it over over the prices here, then you stay submodular. And this is the whole proof. So we get that this coalitional value function is submodular. So I don't know. To me, this proof is it's cool because it's it's so short and it's neat and it shows that once you have the definitions, you can, in a few lines show something that's very fundamental. I also find it a bit, I don't know, not enlightening for me, with my CS background. So I guess something between an open question and, I don't know, an exercise is to give an alternative proof that is more, CSy. Okay, so now I want to quickly show necessity. So here I want to start out with evaluations that is non-GS and show you how to build a market which for which the coalitional value function is not submodular. So let me show you one fact that we'll need. If we take this valuation, any valuation V, and an additive valuation P prime, and we look at coalition of these two players. So it's a little bit weird that I'm using P prime for the valuation, but this is because the valuation is going to be based on prices. So, price vector and a additive valuation, it's really the same mathematical object. It's just one number for each one of the items. Okay, so I'm going to use this P prime for the additive valuation. And if I apply a coalitional value function to it, we already know this. It's minimization over price vector of the utilities. And it turns out it's not hard to see that this minimum is going to be obtained exactly at P prime. Okay, so what we get is an expression for the coalitional value function, which is the utility of the player with valuation V under prices P prime plus revenue under prices P prime. It's hard to see immediately, but the proof is just a few lines. Okay, and this actually generalizes to coalitions with several additive valuations So if you take this player with V and you take several players with additive valuations, the same thing holds if you take as the minimizing price the join of all of the additive valuations. Okay, so on the next slide, let's see how we use this. We're starting with V that is non-gross substitute. This means that its Fenchel dual is non-submodular. So if I take two prices, P and P prime, I do not have submodularity. I can write, I will have some two prices such that the submodularity inequality holds the wrong way. So the utility with the join and the meet is actually more than the utility with the original prices. Okay, I add three additive buyers who have valuations based on these prices, the joins and the meets. And then I can use what we had on the previous slide to write down in a different way the coalitional value functions. And this gives me exactly what I want, because notice that what I have here in black, these are just additive things. Okay, they're just linear, so I have equality here between the two upper lines and the two lower lines. These things in blue here, this is what we assumed that comes from non-submodularity. And then you get the contradiction to W being submodular. So the idea here was not for you to follow every line, but just to see how the proof is relatively very simple once you have this tool of the Fenchel dual and so on. OK, so any questions up till here? So we've covered equilibrium prices forming a lattice. We've covered VCG having really nice properties. And what I want to show you now is that prices coordinate typical markets. But first, I was told that talking for an hour and a half without any break in the middle is too much. So here's a riddle. How is Fenchel connected to this building in the picture? So I guess first, what is this building? You're cheating. OK, but what's the building? Right, so this is a Dan Hotel in the Tel Aviv coastline. It's I think if you've been to the beach, you can't really miss it. And the connection is, it turns out that Fenchel is a German-born Jewish mathematician. Following Nazi suppression, he settled in Denmark, but then his brother settled in Israel and became a renowned architect, and he's responsible for this building. Yeah, so what you can get from Google when you're preparing a presentation and you're bored. A convex set. OK, so next time you're in Tel Aviv, look for this building. OK. So now I want to show you something really interesting, because it's a result that's not classic. It's from last year. It was discovered in parallel by two groups, one of them with Renato and one of them with Alon sitting here. But it seems to me that it's really fundamental. So let's see what you think. So it goes back to a question that was, OK, the question is recent. So do equilibrium prices coordinate markets? But this goes back to theory of Hayek from 45. And he was considering whether free economy versus centralized economy, and trying to argue for free economy. And what he said is that if you have a system in which the information is dispersed among many different players, then you need to coordinate their actions somehow in order to maximize welfare, and this can be done by prices. This can be achieved by prices. And the concept of a Walrasian equilibrium seems to be exactly that thing, right? You have this vector of item prices. Every one of the players acts in a selfish way. They take whatever is in their demand, but somehow magically the demand is not lower than the supply. It's not higher than the supply. The market clears, and this is perfect. And you get welfare maximization by the first welfare theorem. So it sounds like the question is closed, but actually it's not. So let's see a bad example. In this example, we have three players, three buyers, and we have three items. The players are all unit demand, Each of them, if there's an edge between a player and the item, it means that the player wants the item. And the values are all 1. OK. Now let's say that we have a vector of equilibrium prices, P1, P2, P3. Without loss of generality, this is their order. And let's see what happens. So the first player here will want item 1 because P1 is the lowest. The second player will also want item 1, or sorry, I should say could want item 1, right? Maybe the prices are the same, but this is very reasonable for this player to demand the first item. And then what I get is over demand. So I have equilibrium prices, everything should work well, but still I get over demand. So what's going on here? What's wrong? The problem is that I have here 2 welfare maximizing allocations. Here's the first one, and here's the second one. OK. It turns out that you have to have uniqueness for coordination. You have to have uniqueness of the welfare maximizing allocation for coordination. By the second welfare theorem, equilibrium prices will support any welfare maximizing allocation. By supporting an allocation, I mean that if you take the prices and the allocation, this forms a market equilibrium. So I don't think we talked about this theorem very much, but it's just by the linear program duality. You can take any mix and match the primal optimal solutions and the dual optimal solutions, and everything should work. OK. So this is just to show you an example. Let's take these equilibrium prices here. And notice that they have to support the two welfare maximizing allocations. And so necessarily in the demand of a player, there are two different subsets of items. And this means that the prices are potentially not coordinating. And so we see that uniqueness of welfare maximizing allocation is necessary. And it turns out to be also sufficient. So to state this formally and show you a sketch of the proof, let me define what it means for prices to be coordinating or robust. Well, we say that they're robust if every player has in his demand a single bundle, given these prices. Of course, if you have robust prices, this is definitely coordinating the market. Every player just chooses one thing. OK. And here's the theorem that I was mentioning that I think is pretty fundamental. If you have a GS market, uniqueness of the maximum welfare allocation is sufficient for the existence of robust equilibrium prices. We already saw it's necessary, but this theorem says it's sufficient. It even says more, almost all equilibrium prices are going to be robust. OK, so what I want to do now is show you a quick sketch of why uniqueness of welfare maximizing allocation is enough for existence of a robust pricing. And then I'm going to argue why I think this condition of uniqueness of welfare maximizing allocation is very natural and benign condition. OK, so here's a proof sketch. I'm going to start by assuming the uniqueness of maximum welfare allocation, assuming growth substitutes. And what I'm going to show is that there exists a ball of equilibrium prices. This means that I'm going to have some equilibrium price P, equilibrium price vector P, that if I change every one of its coordinates a little bit, I stay in the ball, so this is still an equilibrium price vector. Why is this enough? Because let's see why this means that this P here has to be robust pricing. Let's assume for contradiction that it supports, in a player's demand, 2 bundles. One of them is the bundle that actually corresponds to the welfare maximizing allocation. Let's call this S star. And the other, some other bundle, let's call it T. OK, so we have 2 bundles. Let's say, this is without loss of generality, that there's some item in T that's not in S. They're not the same bundles. And you can deal with a symmetric case in a similar way. So now we start with P, and we decrease a little bit the price of this item here. And what happens is that we stay within the ball. We stay in the equilibrium price ball. So P prime is also supposed to be an equilibrium prime. It should support S star. OK, otherwise it's not going to support the welfare maximizing allocation. But actually, because we lowered the price of J, now only T is the thing that this player demands. OK, so showing the ball is enough. This is what we're going to do in the next couple of slides. We're assuming the uniqueness of maximum welfare allocation and gross substitutes, and we're showing a ball of equilibrium prices. OK, so this is the next 2 slides. And this, I wanted to show you this proof because it shows where the tool that we saw in the first part of the talk, first part of the tutorial, this exchange graph of Murata, how it's used to prove this theorem. So let's remember what was the exchange graph. So the exchange graph is with respect to a particular allocation. In this case, of course, I'm taking the unique maximum welfare allocation. I have one node for every one of the items. And I'm also adding dummy nodes, which correspond to the players. And what are the edges? So if I look at all of the items that are allocated to a certain player plus the dummy item, then I'm going to add edges from each one of these items to all the other nodes. And now the weights. Let's look at these 2 bold edges from the orange to the strawberry into this black player here. And these tell me how much this pink buyer would lose if she exchanges the orange with the strawberry, or if she just gives up the orange in favor of the black player. This is why I need the dummy items. OK, so this is just what we saw in the previous part, restated. OK, now a theorem that we saw in the previous part is the following. So in this exchange graph, there exists a potential where a potential is a function on the nodes such that the weight on every edge is at least the difference in potentials. So there exists a potential if and only if there's no negative cycle in the graph, if and only if minus these potentials are equilibrium prices. OK, actually this theorem can be strengthened. Let me just mention that because we're working in a gross substitute market, clearly equilibrium prices exist. And so we already know there are no negative cycles in the exchange graph. Now I can strengthen the theorem a little bit and show you that, there exists a ball of potential or a ball of equilibrium prices if and only if there are no negative cycles and also no zero cycles. So all cycles are strictly positive. And this completes the proof because I already know there is no negative cycle, and I claim there's no zero weight cycle. If there were a zero weight cycle, you could take the minimal such cycle, and if you follow kind of this cycle, which is basically shows you a way to exchange items among the players, this will give you another allocation, which is also welfare maximizing. And this completes the proof because it means that all cycles are strictly positive, and so I have a ball of equilibrium prices, which is enough for robustness of prices, as we saw. OK, sorry. So this is a sketch. OK, any questions about that? So here's why I think it might seem like a very strong condition, having a unique welfare maximizing allocation. Does this ever happen? Is this typical in gross substitute markets? So I claim that it is, and this is a claim that's a bit hard to make. How would you say that a typical market has some property? So I argue that a market typically satisfies some condition if you can start from any arbitrary market, perturb it a little bit, add some random noise, and then you get to a market which has this property with high probability. And the idea is a little bit, like smooth analysis. If you take an instance and you perturb it a little bit, your running time maybe is good. So here, the same thing here. You take the market, you perturb it a little bit, and you get this good property of having a unique welfare maximizing allocation. There's an extra challenge here, because if you start with a gross substitute market and you add a little bit of perturbation, do you end up with a gross substitute market? I mean, who says that happens? That doesn't hold in general. So we have to come up with a model of perturbation that maintains gross substitutability. And actually, there are two such models in the literature. So for simplicity, I'm going to focus on unit demand valuation. And I'm going to show you two ways to perturb this unit demand valuation. The perturbation is going to be some additive valuation. And let's see the two ways. So the first one, I look at the original value for any bundle. I look at the perturbed value for the bundles, and I just sum them up. Okay, so this means I change the original value for every one of the possible bundles. The result, this V prime, it's gross substitutes, because gross substitutes is closed under addition of an additive function. It's a little bit like just changing prices or something like this. I mean, it's a little bit maybe strange that you start with something that's unit demand and you end up with something that's not unit demand. And then the second way to perturb does maintain unit demand. You start with V. For every one of the items, you get V prime by adding a perturbation to every one of the values of the items. And for the perturbed values, now you take a unit demand function over these. So this is great, but the problem is how do you define this in general? So it works for unit demand. It actually works for any matroid-based evaluation, like Renato was mentioning, but in general, it's not even well defined. Okay. So here's an example of the two perturbations. If you start out with the unit demand valuation, let's say that V1 is larger than V2, so this player wants the pineapple more. You have some additive valuation, which is the perturbation, so A1 and A2. And here are the two ways. So in the first one, let's look at the value for the set of all of the items. In the first way of perturbing, you now have your original valuation for everything, which was V1. And you added the valuation of this player for all of the items, which is A1 plus A2. But if you use the second way, then you first perturb the value for the pineapple and the value for the strawberry separately. And then you take the maximum among these. So you get V1 plus A1. OK, so these are two ways. And here's the bottom line. It was shown that both of these ways are give you, for a sufficiently small perturbation, for a sufficiently small additive valuation, you get, with high probability, a perturbed market that has unique welfare maximizing allocation. And moreover, the perturbation can come from a discrete range, which is nice because it has some nice properties. Like if you start out with a market with integral values, you can stay with integral values and so on. OK. So yeah.
Just a comment on the model. I don't believe that actual value is hugely precise.
So OK. So do you think this is convincing or not convincing? Someone not, because it can work both ways. Like what I'm trying to say, I think, is that if you don't believe that the valuations are very precise, you believe they're in some sense generic, perturbed, or whatever, then the equilibrium, the welfare maximizing allocation will be unique. Or you're saying we won't see gross? Are you saying we won't see gross substitutes markets ever? Which is great because this is what I'm going to talk about now. I mean, I think what I'm saying is actually it is in the spirit of what you're. What I'm trying to say is that if you look at the set of all markets, most of them are going to have a unique welfare maximizing allocation. You have some pinpoints of markets that don't, but if you perturb them a little bit, you go a little bit around them, then you're going to have unique welfare maximizing allocation. Yeah, so I don't know if this is. So you don't really need to add, the addition of the noise is just for the sake of the proof. It's just proving that a generic market or a random market will have a unique welfare maximizing
The
operation.
question is, what is base set? And what I'd be saying is that coming from, let's say, small numbers, numbers with few bits.
So like integers.
On
But
small
this,
range.
right. So as I mentioned, so you have a this kind of perturbation does work for integers.
Yeah, but you should take off.
Okay, yeah, no, but it's an interesting discussion. Okay, so definitely, I think this is this raises questions. Yeah. That's a great question. I don't know. Yeah, that would be really cool. I don't know. Okay. Mhm. So what do you want to prove analytically? That okay. Yeah, good question. Again, I don't know. I think this whole direction of what is a typical GS market, it's as you can see, it's not well developed yet, but I think it's super important.
I think another way of asking that is, does the high probability mean for every market that doesn't have a unique maximum allocation and for sufficiently small perturbation, does it have a high probability unique maximum allocation, or is it like randomly over all markets with high probability?
It's for any market.
Yeah, that should mean that it's randomly.
Yes, perhaps, yes. Yeah, I tend to agree. But I haven't seen this phrased as that statement. Okay, what's next? What time is it? Okay, so let me skip that slide. I think we're more or less happy with the three market design implications of GS. We saw that prices form a lattice. We saw that the VCG outcome is really nice when we have GS and not nice when we don't. And we saw that prices coordinate typical markets. This raised more questions, which is good because now I'm going to talk about more open-ended topics. Okay. In the first part, we saw algorithmic properties of GS, and we saw that, in particular, GS is a frontier of tractability for problems like demand and welfare maximization. And then now we saw these nice economic implications, including the existence of equilibrium prices. And the question is there some direct connection between the algorithmic and the economic properties? So here's one result in that direction, and I think this is a good direction to work on. I'll show you a direct connection between market equilibrium non-existence and computational complexity of demanded welfare maximization. This is a result Renato was referring to in the first part. Okay, so remember that market equilibrium has two conditions, that every bundle is in, a player gets a bundle in his demand, and then the market clears. And they're related computational problems. So let's fix V to be some class of valuations. And the first problem is just for a single buyer. This is a demand problem, gets some input valuation from this class V, gets the price vector, and needs to output a bundle in the demand. Another computational problem is welfare maximization. This is for a market, for a set of gross substitute valuations, or a set of valuations in general. This you get as an input set of valuations, and your output needs to be a welfare maximizing allocation. Let me skip actually revenue maximization, but you can imagine this is also a computational problem. You can rewrite these two conditions for market equilibrium using these computational problems. So for every one of the buyers, the allocation to this buyer should solve the demand problem. Oh, I do use the revenue maximization. I knew I wanted to say something about that. So thinking of market clearance, you can think of it about it as maximizing the revenue given a vector of prices, because you're just trying to. It's a really simple actually problem when you have vector of item prices. You're just trying to sell all of the items with non-zero prices. And it can get much more complicated when the prices are more complex than item prices, but I don't want to go into this. Okay, and here's a theorem. So the point I'm trying to make is that market equilibrium is tied to these computational problems. And here's a more formal connection. A necessary condition for guaranteed existence of a Walrasian equilibrium for class of valuations phi is that demand is at least as computationally hard as welfare maximization on this class of valuations. And an implication is that if welfare maximization is harder than demand, for this we of course need some kind of assumptions like P is not equal to NP, then equilibrium existence is not guaranteed for this class of valuations. And I want to show you a quick example. So let's say that this class of valuations is capped additive valuations. Without going into the details, if you're trying to maximize your demand and you have a capped additive valuation, then really what you're trying to do is fill a knapsack with items that you value until your cap. So it's equivalent to knapsack. If you're trying to maximize welfare with a bunch of these valuations, it's very similar to the bin packing problem, and you can show that it's computationally equivalent. This one has a pseudo-polynomial time algorithm. This one is strongly NP hard. So we have the separation under P does not equal NP between the two computational problems, which means that there is some market with capped additive valuations that does not have a does not have a market equilibrium. So this is the way you can use this theorem. And the relation to gross substitutes is, of course, as we saw, it's exactly the frontier of tractability for demand and welfare, and this is in welfare maximization. And this is very suggestive that maybe the reason that we have existence of a Walrasian equilibrium for gross substitute is somehow this relation to computational complexity. So a few pros and cons of this approach, and where I think the open questions are. So the con is, of course, you do need the computational assumptions. And then the pros is that it's an alternative to the maximum domain result. We know that equilibrium existence is not guaranteed for a class of valuations, which includes unit demand valuations, unless this class is gross substitutes. This is something Renato mentioned. But it turns out that a lot of classes of valuations that we might be interested in do not include unit demand valuations. So I've listed a few here. So it's good to have an alternative, and this approach gives you an alternative. It also generalizes to relaxed notion of equilibrium to typical markets. And then I think an open direction is to take the complexity approach and apply it to other economic properties of GS, and maybe this will help us to show necessity of gross substitutes or necessity of the algorithmic properties of gross substitutes for some of the nice economic results. Okay. What I want to do now is talk a little bit about pushing the boundaries. So what I thought you might be saying at first is that This definition of gross substitute, as remember from the first part of the talk, it's really, it's a bit delicate, and it seems a bit unreasonable that valuations will exactly be these of this type. And so the question is, do we get the nice properties more generally? And I want to motivate this by the following mystery, which comes from the last year's incentive auction. So I don't know if you heard about this auction. It was very much celebrated. This is a quote that calls it groundbreaking or revolutionary, first in the world. This is actually from the FCC blog, so I don't know, you can take it with a grain of salt. But it was also awarded, it's also just the fact that, it's a $20 billion auction, and it freed up a lot of spectrum that is needed for wireless communication. And it also won this year's Franz Edelman Award at Informs. So an important application. And I want to show you a mystery that's related to it. Okay, so in the incentive auction model, we have, here's what's going on. So we have TV broadcasters, and each one of them has a value for staying on the air. But we want to clear up spectrum. So the outcome of the auction is going to be the set of broadcasters that we managed to get off there, and then the set of broadcasters that are staying on the air. And I'm going to denote this by capital A for air. They're staying on air. Now we're going to have to repack this set A to a reduced band of spectrum. And so formally, we can define a feasibility constraint on the set of broadcasters that can be feasibly repacked according to the amount of spectrum that we have left, and maybe some other constraints, repacking constraints. So notice that an outcome of the auction is going to be feasible only if these broadcasters that stay on the air are feasible. And also this set is downward closed, because if you can repack a set, you can always repack a subset. So here's a picture. Each one of these squares is a broadcaster. I wrote down their value for staying on the air. Some of them are going on the air, some of them are staying on the air, and some of them are going off there, some are staying on the air, and they're repacked according to some constraint, maybe like a knapsack constraint. Maybe they have to fit into some limited space. Okay, our goal is going to be to minimize the total value that goes off the air, this one, or to maximize the total value staying on the air, subject to this feasibility constraint. Okay, so this is the model, this is a really, really complicated auction, so I'm simplifying a little bit, but really this is the heart of the problem. So mathematically, I just want to write, here's our problem of finding a set which is feasible and has maximum value. Okay, now, first fact, if you want to maximize a feasible set, its total value, you can do this by greedy if and only if the set is the feasibility constraint that defines a matroid. Okay, we talked about this in the first part. Equivalently, you can define a valuation function that is really the rank function of this feasibility set system, and this has to be gross substitutes. Second fact, this feasibility set in the actual auction, it's not a matroid. And third fact is that a team by Kevin Layton Brown and his collaborators were working on this, and they actually designed what happened in the incentive auction. And they ran some simulations, and when they sampled values according to FCC predictions, it turned out that if you maximize greedily, so if you greedily choose who stays on the air and who goes off the air, this will achieve 95% of opt on average. So this is really weird. So we have something that's not a matroid, but greedy works really, really well. And I think, so the question that it raises is, do we have some way of saying that these feasibility constraints are 95% a matroid, or that this valuation is 95% a gross substitute valuation? And it ties into a higher level research agenda. So as I mentioned, or as we saw, in theory, only gross substitute markets work really well. and have the good properties that we discussed. The belief is that markets actually work well because they're somehow approximately gross substitutes without really defining this. Or in other words, that the good properties are robust to deviating a little bit outside of gross substitutes. And the agenda is that we need theory that predicts when markets actually work well. So this is the kind of theory that we want. To develop this, we need good models of approximate GS. And it ties into the beyond worst case agenda because if you just replace markets here with algorithms, it's the same goal. You know, we need the theory that explains when algorithms actually work well, and not just in worst case. Okay, so my plan is to show you two approaches to defining approximate GS. And this is really, recent work, and you'll see it's not, it doesn't close the question. So it's a starting point for further research. So the first approach is very natural. I think it's kind of what Renato was saying in the first part. So you focus on the fact that greedy works well, and you ask for what evaluations, or for what combinatorial structure does greedy provably get me 95% of the optimal value. And then the second approach is going to be, forget gross substitutes. It's too difficult. Let's not work with this for now. Let's just look at linear evaluations, really, really small subclass that's really easy. And let's try to perturb this a little bit and see what happens. Okay, so first approach. I'm reminding you of two characterizations of matroids. If you haven't seen matroids, this is not going to be very useful, but just kind of to remind you of two properties. The first one is that in a matroid, if you take any set of items and you take two feasible subsets of the items, then any such two subsets should have the same cardinality. So you can write this as something called the rank quotient. You take the minimum over all subsets of items, the minimum of this ratio, and it should be 1 if it's a matroid. This is a characterization. And the second characterization is the exchange property. So if you have one feasible set that's larger, one that is smaller, there's some item j that I can add to the smaller one, and everything will stay feasible. And now I'm going to show you on the next slide how this changes when I define an approximate matroid. So let rho be the parameter that is the approximation parameter. And you can see that this rank quotient is now rho. Rho is maybe some 0.9 or 0.95 maybe. Instead of 1. Or the rho exchange property, which is saying that if A prime is much larger than A prime, if A double prime is much larger than A prime, then they have this exchange property that we were mentioning before. Okay, so this was actually known, this is known for a long time. And if this holds, if I have this rho matroid structure, this is an if and only if condition for having this problem that we were interested in being rho approximable by greedy. Okay, so this is a characterization of the combinatorial structure that we need for greedy to get us 95%. I should mention there are alternatives. So Paul Milgram has this recent notion of being rho close to a matroid, and he shows that if you use greedy for the matroid that you're rho close to, then you also get a good approximation. So I guess I guess this is not the only way to. This rank quotient thing is not the only way to approach it. And it raises a few questions. So let's say we are convinced by this rho matroid definition. Do the GS nice algorithmic properties extend? For example, can you maximize welfare up to 95% if you have a 95% matroid? So we know that demand works, right? We saw this greedy gives you 95%, but the question is, what can you get for welfare? And then, so alternative approximation notions. And also, maybe most importantly, looking at the empirical side. So we know what the constraints are, for example, for the FCC incentive auction, and we can look at them and we can find out whether this is an approximate matroid or not. And if not, maybe we can get clues for what's driving greedy to work so well. Okay, so that was the first approach to approximate gross substitutes, and here's the second one. So, so as I said, let's just forget about gross substitutes. Let's look at linear evaluations. Just to remind you, this is a valuation that is defined by one value for each one of the items. And the value for a set is the sum of the values for the items plus some offset. Why linear? Well, it's fundamental, but it still raises a lot of open questions. It's equivalent to modular. So valuation V is linear if and only if the modularity equality holds. Well, you might be annoyed by this offset. Well, it turns out that additive valuations are too easy in a sense I can mention later if you're interested. Okay, so if I'm focusing on linear evaluations, now I want to study natural approximations. So what would you consider to be a natural approximation of a linear evaluation? Here are two ways. So first of all, you can have some pointwise approximation. This also is divided into two separate ways. So you look at the valuation. It's a long vector of exponentially many values, one for each one of the subsets. So you can just additively perturb this, or you can have something that's close in a multiplicative sense. So this is the multiplicative sense, and this is the additive sense. What I've drawn here is the additive sense. So I've drawn. Actually, this is for a symmetric function because I can't draw the high dimensional one. So on the x-axis, I have how many items in the bundle. Here I have the value for the bundle. And you can see that this V here is a perturbation of the V prime, which is linear. Okay, so this is the additive way. And then another way we can think about is, we said linear is equivalent to modular. So we can have the modularity inequality hold up to epsilon. Okay, so what's known about these ways to approximate linear? Not very positive results. First of all, if you have V prime, which is a 1 plus epsilon approximation, now V is going to be the 1 plus epsilon approximation, and V prime is linear. I'm working with V. So if I don't query V at least exponentially many times, I have no hope of getting a constant factor approximation of the maximum welfare. So this is bad news. I'm trying to work with the most natural approximation I can think of linear functions, and I can't hope to get anything close to maximum welfare. What we are able to show is that if you're also approximately submodular, then you can get some approximation that depends on both how far you are from the linear function and how far you are from submodular. And this is kind of maybe reminding you a little bit of the valuation hierarchies. So, so we have, we know some good things happen if you're close to submodular. And what the result I just mentioned shows is that if you are close to gross substitutes, but you're not close to submodular at this point here, then you can't do anything. But if you're in some sense close to both, then there's hope. Okay. Now, that was a mostly negative result. So what about approximate modularity? Maybe we can do more here. So it turns out actually that V is epsilon approximately modular only if it's pointwise in the additive sense, constant times epsilon approximation of a linear valuation. So that means that because we have the bad example, because we have the impossibility results for something that is pointwise close to a linear valuation, and these two things turn out to be equivalent, then approximate modularity is not helping us either. Okay, so to summarize what we just talked about, we have this mystery of the incentive auction. It really works really well, even though it's really not supposed to. And the ways that this has been approached is look at approximate matroids, and I think this needs more research, and then to look at approximate linear evaluations. And here it turns out that the algorithmic properties are not robust to very natural approximation notions. Okay, but I think this is, it's super important to solve this mystery. Why greedy works in practice. It's going to be hard given these initial results, but it's very important. Okay, let me actually skip. There are other worst case approaches. Let me actually skip these now. I want to tell you just a little bit about what's going on in econ right now. So if you've been coming to EC for a few years, there's always a few talks on more and more intricate models of gross substitutability, for example, for trading networks. And so this is, I'm not by no means an expert on this, but I just want to give you a taste of what's going on. I think that the fundamental paper here is a paper called Matching with Contracts. So what the status was historically, there was, for example, if you take a look at the two-sided matching book of Roth and Sotomayor, you're going to see that models with and without money were separated. So the results were really similar, but the treatment was separate. And this paper, the Matching with Contracts paper, unified the models. And now you have one model which captures, for example, doctors in hospital, which is a classic matching without money scenario. And you have the same model capturing combinatorial auctions. And the way this works is you have these objects called contracts, which are bilateral. And they tell me, first of all, who is matched to who, and also what the conditions are, for example, wages in the job market. And substitutability plays a really important role in the results here. And then after that, there was a really, really long line of research, so I can't really even start to cover everything. I think the most recent one is this paper by Hatfield et al. It unifies, I think they say, 8 different substitutability concepts for an individual agent. For markets, they unify stability and equilibrium concepts. What I want to do now is show you, I think, maybe the most general model that people are working on right now, and this is called trading networks. This is a multi-sided setting, so we had like bilateral setting, and then anyway, this is multi-sided in the sense that you'll see now. The trading network has a node for each one of the agent. And now I say agent and not say buyer or seller, because an agent can be a buyer in some trades and a seller in others. We have a directed edge between the agent if there's a trade going on between them, where this side of the edge is the seller and the side with the incoming edge is the buyer for that particular trade. And then everything is kind of familiar. The valuation function is now over sets of trades. And you have the prices for every trade. Prices are on the edges. And you have quasi-linear utilities. So for example, this player here, his utility is going to be his value for the 2 trades that he's involved in, minus what he has to pay for what he buys, plus what he is getting paid for what he sells. So this is the model. And without really going into the details, just what are the main results in this area of research. So it's a lot about market equilibrium existence, and also about showing that equilibria are equivalent to stable outcomes. Stable meaning that they cannot be blocked by coalitions of trades. And it's interesting that it's sufficient to look at blocking paths and cycles and so on. And a really nice paper here is by Kandogan et al. And they show equivalence of this model to a network flow model, where equilibria correspond to optimal flow in the dual, and the stability corresponds to no improving cycle. So you can kind of see the connection intuitively. And this also has algorithmic implications for finding the equilibrium, for example, in such a trading network. So kind of everything Renato said in the first part, we can now apply to a trading network and try to figure out how do you find the maximum welfare allocation and so on. Okay, or sorry, I should say maybe maximum welfare set of trades. Okay, last thing I want to tell you about, and I'll just, actually I think I don't have time. Let me skip this because I want to summarize. Okay, so the main takeaway maybe from this part and maybe from the whole tutorial is that there's much more to study when we're considering growth substitutes. So I hope I convinced you that there are some recent results that have a very fundamental flavor to them. So there's still fundamental theorems to be uncovered. For example, this unique welfare maximizing allocation theorem that we saw. It has strong ties to algorithms, so I think it's a good time for computer scientists to be working on this. For example, this trading network idea that is exactly like network flow, or these computational complexity implications for equilibrium existence. And then there are open crucial puzzles that have a practical flavor. So this way beyond worst case performance of greedy in the incentive auction setting. And that's it. Any questions? Okay, thank you so much.